This lesson is on geometric series. This means we're going to be looking at sums of terms in geometric sequences. What are geometric sequences? Well, they're sequences where each term is multiplied by a common ratio to get to the next term. So let's first consider finding a partial sum, and then we'll move towards looking at an infinite sum of the terms. In the arithmetic sequence, remember, there was no infinite sum. Infinite sums just ended up being infinity. However, sometimes with a geometric sequence, you will be able to find an infinite sum, but sometimes you won't. Let's start with a partial sum, which we can always find. And let's start with an example. So say the first term is 1, the next term is multiplied by 3, and then multiplied by 3, and then multiplied by 3. And now I'm going to write out all the following terms up to 8 terms, and we're finding the sum of the first 8 terms. Okay, so what has been found is that to add these up, obviously you could type them all in and add them up. However, you can imagine that S8 could be an S20 or S100, and what are you going to do then? That's going to be an astronomical amount. So there has been a method that's been devised, and I just want to share it with you. You don't need to remember to use this method, but it's more of an interest, a point of interest to take a look at. So it has been found that if you take the S8 and then you subtract R times S8, which in this case is 3 times S8, what this does is each of these terms becomes multiplied by 3 and negated, which when we add them up together is going to cancel out a bunch of terms. So if we subtract 3, subtract 9, subtract 27, subtract 81, subtract 243, and so on. And finally, we're going to subtract the 3 to the power 9 term. And what this does is we end up canceling out these terms, and we're left with the first and the last. And so therefore what we have is S8 minus 3S8 is equal to 1 minus 19,683, which is negative 19,682. Now factor out the S8, we're left with 1 minus 3 here, and so we have this number divided by the negative 2, leaving us with S8 equaling 9,841. And you can check that and see if it's equal to the first row there. So you can see this generalized pattern, taking the Sn and subtracting R times the Sn, therefore getting rid of all these terms, leaving you with the first term and one more times in terms of the power of R of the first term than you had of the last term of that sequence. So what this leads to is we have Sn minus Rsn is equal to A1 minus A1R to the n. And we can factor out the Sn, leaving us with 1 minus R. And then we can divide by 1 minus R. Therefore, solving for Sn. And so this is our formula, which works for any R that's not equal to 1. As you can see, if R was 1, our denominator would be 0. So we can't use the formula for that. But any partial sum, meaning has a limited number of terms, with a geometric sequence, with a rate, the first term, number of terms, you can use that formula. But what about an infinite sum? So we know that this is true for the partial sums, but let's consider what happens at different places of R. So if the rate is less than 1, plus or minus because of the absolute value, let's consider what would happen. So let's say you have a1 being 4 and the rate being 0.5. That's less than 1. It could be negative 0.5, but that was just change the signs. No big deal. So that would be like 4, then half of that, and 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 so on. And you can see that the numbers get smaller and smaller. So yes, for a partial sum, you can still use this, of course, no problem. But for an infinite sum, you'll notice that these numbers get so small that there will be an answer to what this equals, even though it becomes infinity, because the numbers just get so small that eventually they don't really add to much more. There's a limit. But what if the rate is greater than or equal to 1? Well, let's consider the equal to 1 bit, because obviously you can't find the partial sum for that with this formula. First, let's consider, say you had the same thing here, a1 being 4, but the r being 1. Well, what does that mean anyway? Well, that means that every time you're multiplying by 1. So you just have however many first terms you have. So if you're trying to find, say, S8, you'd say 8 times 4, and that's it. So you don't need this big formula for that. But if you're trying to find S infinity, that's going to cause a bit more of a problem, because 4 plus 4 plus 4 plus 4 to infinity is going to become infinity. So if it's equal to 1, it's going to go on and become infinity. If it's greater than 1, what do you think? Well, if a1 is 4 and r is, say, 2, well, that's going to be 4, 8, 16, 32, and it keeps going, and it becomes bigger and bigger, and yes, of course, it's not going to converge to any numbers. It's going to grow exponentially, and if you add them all up, it's going to end up being infinity as well. So we have a problem when the rate is greater than or equal to 1, but for an infinite amount of terms, we can find the answer as long as our rate is smaller than 1, meaning it's shrinking. And that should become obvious that if it's shrinking, then you can find the answer. Now let's take a look at this formula, and how is this formula found? Well, what happens if the rate is really small? Well, let's consider this formula that we had here, Sn, a1, 1 minus r to the n over 1 minus r. But instead of n being n, it's now infinity. So what happens when you take a very small number to a very big number? So say, for example, 0.5 to the power of, say, 100,000, right? Try that on your calculator. What do you get? Or it actually gives you 0. So you can see that as it gets taken to a higher power, this part becomes a big 0, leaving it with a 1, therefore leaving it with just a1 over 1 minus r as the infinite sum. Remember that if it's greater than 1, the sum does not exist because it diverges and becomes too big to answer. So let's take a look at what this looks like on a graph. What I've typed in here is a set of natural numbers and then the plot points of 2 times 0.5 to the x minus 1, which is a geometric sequence represented with first term being 2 and then 0.5 being the rate to the x minus 1 to be the terms. So you can see that they get closer and closer to 0 as you keep going. And that's if it's 0.5 as the rate. But what if it's 1? A rate of 1 is constant. And what if it's 1.1? It starts diverging. So it continues up and up and up. And so you can play around with this. Obviously, if your rate is very small, it gets really small really quick. But if your rate is, say, even 0.99, it's still going to get closer eventually it's still gonna come down. So let's see what happens to it if this gets big. It's going down. So it goes down slower, but it will go down versus staying at 1. So let's use this to find some sums. So here we've got S12. We want to find the first 12 terms. We've got a geometric sequence with rate 2/3 and first term 5. So our S12 is going to be our first term times 1 minus the rate to the power of n, which is 12 in this case, and it's going to be 1 minus 2/3 in the denominator. Now you just have to be careful with putting this into your calculator, so make sure you include all the necessary brackets. And what you should get, try this out, make sure you know how to type it in right, is 14.88, which says, say it's rounded to 14.9. Now let's try this next one. What's happening here? It's a geometric sequence, we've been told. So our first term is 3, and what's our rate? Well, it's being multiplied by 2. So S12 will say the first term is 3, 1 minus the rate to the power of 12 over 1 minus the rate. And so that gives us 3 times negative 4095 over negative 1. So it's really just 3 times 4095, which is 12,285. Isn't that much easier than finding all the numbers and then adding them? So let's take a look at this next example. Evaluate the series. The series could be written like this. Remember, this means that it starts with a 1. So our A1 term is 5 times 3 to the 1, which is 15. And our rate, every time we move from that term, we're multiplying by 3 now. So the next term will be 45, and so on. We'll multiply by 3, and we'll take the first 5 terms and add them. In this case, it's not too difficult to find the first 5 terms by hand, but let's try our formula out and see how it works. So S5 will have first term times 1 minus the rate to the power of the number of terms over 1 minus the rate. And what does that give us? That gives us 1,815. Which is the sum of the first 5 terms, starting with 15, where each term is multiplied by 3. Now, what about this next one? This one has an infinity sum, and if this rate here was greater than or equal to 1, we would not be able to find the answer to this. The answer would not exist. But in this case, we have a rate that is less than 1, which is great. So that means we can use our S infinity formula, which is A1 over 1 minus R. It basically just skips out on that bit. So what's our A1? Our A1 is 3/5 times negative 1/2 to the power of 1. So we can simplify that. We get negative 3/10. And what's our rate? Well, our rate is negative 1/2. So let's plug that in. So we have negative 3/10 over 1 minus negative 1/2, which will be negative 3/10 over 1 plus 1/2, which is 3/2. So then we can, for the division, multiply by the reciprocal, simplify, and we get negative 1/5. Now let's take a look at an application. If you have a ball that's dropped from a certain height, and it rebounds 3/5 of the original height, how high will the ball rebound after the 4th bounce if it's dropped from a height of 10 feet? Meaning the initial bounce is 10 feet. And then it goes up, and when it goes up, it's 10 times 3/5. Now that is going to double, because it's got to bounce back the same way. But the next time it comes up, it's going to be 10 times 3/5 squared. And then it's going to go down, which is doubled. and so on. 10 times 3/5 cubed, 10 times 3/5 to the 4th power. So you can develop a formula that will give you the rebound after the 4th bounce. So how does that work? This was after the first bounce. So A1 was 10 times 3/5 to the 1. So after the 4th bounce, that'd be 10 times 3/5 to the 4. So you can find that on your calculator, and that gives you 1.296, which is also seen as 162 over 125. Okay, but what about the total rebound distance before the ball comes to rest? Now this is a little more tricky because that means that sentence implies that we're looking at the total travel until it comes to rest. So it's an infinite sum. So if we find the infinite sum of this sequence that is described by an being 10 times 3/5 to the power of n. Now if we look at all the rebounds, that's going to be given by the formula an is 10 times 3/5 to the power of n. So if we put that into the infinity series calculation, that'll be the first term, which is 10 times 3/5 over 1 minus the rate. So that'll find the sum of all these up motions. Now we'll have to double this because we have also the down motions, and we also forgot the 10 as well. So if we plug that through, that's going to give us the total distance that the ball has traveled the whole time. And that actually ends up being 40. So what's happened is the ball has traveled a total of 40 feet, even if it's still bouncing.